Okay, this is kind of a standard type of example that you can get. It says express as an algebraic function of x. F of x equals tangent of the quantity, the arc sine of 2x minus the arc cosine of x. So the trick here is to recognize that arc sine and arc cosine are both angles. So this is something of the form tangent of one angle minus another angle. So you're going to use the difference identity for tangent, which you could write down on the side at the start as soon as you notice that. I didn't, but you could. So I just make up names for the two angles. I called the first one theta and the second one gamma. You could use A and B if you wanted to, you know, something like that. It doesn't matter as long as you don't use x, because you already have an x. So what I did, this is the trick. You set each one equal to its angle name. So theta equals arc sine of 2x. Now how does that help? Well, that tells you that sine of theta equals 2x. Okay, so we're getting away from the arc sines into something that we can understand in terms of triangles. The 2x sine is opposite over hypotenuse. So you want to think of the 2x as a ratio of two numbers. So you just put it over 1, which we've seen before. So that's opposite over hypotenuse. So you draw a right triangle where the hypotenuse is length 1 and the opposite side is length 2x. Now, they could be in either of these positions. So this is a little bit tricky as to know which one, because x could be positive or negative, right? So it could be in either of these two positions. Actually, yeah, that's right. Yeah, I'm assuming y is positive here because there's actually, it could be in the other two positions as well. There's 4 positions. Anyway, arc sine is always in quadrants 1 or 4. So that's why it's in these two and not quadrant 2 or quadrant 3. So I drew them in those quadrants for a reason. And that means the key thing there is that y is going to be positive. The side I labeled y is going to be positive. Okay. Yeah. So then I use the Pythagorean theorem. 1 squared, the hypotenuse squared, equals the square of the lengths of the two sides. So I had to make up that letter y as well. Otherwise, you'll get stuck if you don't do that. So you get y squared plus the quantity 2x squared. So y squared equals, so if I solve for y squared, I get y squared equals 1 minus 4x squared. And then I solve for y from that, and I know it's the positive y, not the minus. So I don't need plus or minus square root. I just use the positive square root. So y equals the square root of 1 minus 4x squared. All right? So you could just remember, if you're doing this with an arc sine, it's going to be the positive one, I suppose, if you didn't want to reason through it like I did. But we have to do this a lot anyway, figuring which quadrant you're in. With these arc sines and arc cosines, you always have to know what the range of them are, which is what quadrant is your angle in. Remember, the range of the arc sine is the angle. Okay. So I've got what y is for that triangle. Now I have another triangle for the second angle, which is arc cosine x, because that's probably not in the same triangle, right? So I set gamma, or you could use a b or letter b or whatever, but I use this Greek letter gamma equals arc cosine x. And that means I'm going to do the same thing. So cosine gamma equals x. That's x over 1. And cosine is adjacent over hypotenuse. So I draw a triangle adjacent over hypotenuse with x. X could be positive or negative. It's going to be in one of those two. the z will turn out it has to be positive. And the reason is because the arc cosine is always in quadrants 1 or 2. So the z has to be positive. Okay. The original number x could be positive or negative, though. But that really won't matter because we're trying to solve for z. Well, yeah, we're trying to solve for z here. Okay, so notice z is greater than 0, just like y was in the previous one. So we've got the hypotenuse, well, the sum of the squares of the two legs, z squared plus x squared equals the hypotenuse squared, which is 1 squared. Solving for z squared, we get z squared equals 1 minus x squared. And then we know z is positive, so we don't get the plus and minus square root, we just get the plus square root. So z equals square root of 1 minus x squared. And that's really important to know that you only get the positive one. Okay, so now I need to know what the formula is for my tangent of theta minus gamma, so I wrote it out. Tangent theta minus gamma is tangent theta minus tangent gamma over 1 plus tangent theta tangent gamma. So I just need to know what tangent theta and tangent gamma are. That's why I figured out all these triangles. Okay? So tangent is going to be opposite over adjacent. And notice we don't need to know whether the opposite or the adjacent is positive or negative because it's a variable. So we can just use the variable. Okay? So tangent of theta is 2x over square root of 1 minus 4x squared. So it's opposite over adjacent on this first one, tangent theta. This was theta. So I just look at either triangle, doesn't matter. It's the same. The labels are the same. So you've got opposite 2x over adjacent, which is y, which is this thing here. Right? So now I've got the tangent theta written as an expression, algebraic function of x. That's what that's called, the algebraic function of x. Now we do the tangent of gamma, and it's the same thing. It's opposite over adjacent. They're just different numbers. So opposite here is z, which is the square root of 1 minus x squared, and the adjacent is x. And regardless of which triangle you use, it's the same. Notice the labels are actually all identical between the two triangles. Okay, so that's tangent. It's just the opposite of the angle over the adjacent. And z happens to be this. I figured it out from the Pythagorean theorem because you want it in terms of x. Then I have to take these two quantities and put them in this formula, which is a good reason to write this formula out first, right? So I'm going to continue that on the next video.